Okay, so this is Albert doing lab 3 circuits for physics 2212. So the goal of this lab was basically to see how circuits behaved under certain circumstances with resistors, whether they be in parallel or series, and also capacitors added, so RC circuits. And then we're just going to use some multimeters to measure those differences in potential and the currents. So some things you're going to need to know before are the Kirchhoff node rule. The Kirchhoff node rule is just saying that whatever current goes in a junction has to come out. So current in equals current out. And the loop rule is just saying that the difference in any loop around the circuit is always going to be zero. Then you're going to need to know how resistors work. Basically, all you need to know is that delta V, or the difference in potential, is I, the current, multiplied by the resistance R. Then when they're in parallel, it's defined with that equation below. And then when they're in series, you just add up the resistances and keep the same current. Then capacitors, we're going to say that delta V equals Q over C, where Q is the amount of charge on a plate, and then C is the capacitance of certain material. Then we're going to need to assume that the voltage slash current source is constant, so that's going to be our battery. Then we're going to say that the resistance within the wires are zero, and that the resistors and capacitors are ideal, meaning they're perfect. So the things we found were that the currents were 0.02 and delta V was 3V, and that's what we predicted, and that's also what we found measuring. So the first procedure we're doing is basically making the circuit at the top right, and then we're going through each of these steps you can read on the left, basically to see, what happens when they're in series and in the middle, whatever. And just we're recording all of those things, and you'll see our findings afterwards. So procedure 2 involved a light bulb and a capacitor. We basically lit up the light bulb, and then the capacitor filled up. Then we discharged and lit up the bulb again with the capacitor instead of the battery, and timed that to find the time constant and other things. So you'll of course see our results after. So in the first one, using the ammeter, we predicted the current in this formula right there, and then the experimental current was right there. And then when we reversed the current, basically had the ammeter reversed with the positive negative ends, we just got the negative of that. Then with the voltmeter, it was just, predicted current, predicted delta V, everything alike, pretty straightforward. Obviously, according to the loop rule, it's going to be these values. So here's some the potential differences across each thing, each part. They uphold the loop rule. When they're in parallel, the current across the resistor was 0.0544. So basically, just adding another junction, basically just adding another resistor. So that's why the current is a little different. And using that, we calculated the resistance and got pretty close to the resistance said on the resistors. So yeah, that's how we found that. Here is our potential graph. At 40 or at the beginning goes up to 3, then after this one it goes down to 2, then after this one it goes to 0. Then we use our light bulb. Here are our values, time values that we got for charging, discharging, whatever, with the 10 ohm light bulb and the 20 ohm. And using that, we found slope of natural log of of difference of potential divided by initial potential. And then we found that our time constant is 9.9. So any sources of error, it could have been some faulty components, not completely ideal to what they were labeled as, and then timing error for the light bulb, and then some ammeter precision. Of course, we could have had faulty gear. So here's some final thoughts. What if you had a charged capacitor with no resistor? How quickly would our ideal model predict the capacitor to reach full charge? If you charge a capacitor with no resistor, the capacitor would basically instantly charge. All of the electrons would go in, and according to this formula right here, with R equals zero, T becomes zero, so instantly charges up. But this can't really happen in real life because there's always resistance, whether it be in the wire or something else. So the sudden flow of high current would probably blow up the capacitor slash battery too, or battery. And if we were to measure with ammeter, it would be very rapid but not instantaneous because of the resistance, and then it would be but it would still be a huge large spike that would slowly decay. So